Good morning, everyone. In our lecture today, we're going to be exploring a concept from mathematics that, at first glance might seem a bit abstract, maybe purely theoretical. But, as we're about to see, it's actually one of the most powerful and practical tools in any modern manager's toolkit. We're talking about the parabola, and we're going to dive deep into exactly how its shape is the key to unlocking maximum profitability and making truly optimal business decisions.
So, let's start with the big question, really the central question of managerial economics. What is the perfect price for your product? As future managers, this is a puzzle you are going to face constantly. Think about it. If you set your price too high, you could drive away customers. Set it too low, and you're just leaving money on the table, not capturing the real value of what you offer. It's this incredibly delicate balancing act, right? Finding that one sweet spot that maximizes your revenue. And that is the fundamental challenge we are going to solve together today.
For a long time, finding this price point was all about intuition, gut feelings, and frankly, a lot of expensive trial and error. But we live in a different world now, a world swimming in data. And in this world, we can be so much more precise. The best answer isn't a guess. It's a specific, calculable point on a graph that we can find with mathematical certainty. So, let's begin our formal analysis.
Okay, here's our roadmap for today's lecture. First, we'll build that bridge between the concept of a parabola and the goal of profit. Then, we'll dissect the anatomy of a business model using something called the quadratic function as our guide. After that, we'll get into the nuts and bolts, the mechanics of actually finding that optimal point. Then, we'll put it all to the test with a real-world pricing strategy case study. And finally, and this part is absolutely crucial, we'll go over the common mistakes to avoid so you can apply this technique accurately and confidently.
So, let's jump into our first section, from parabolas to profit. I really want you to think of this not as just a math lesson, but as a deep dive into core business strategy. The principles we're about to discuss aren't just some side topic. They are absolutely fundamental to making high-level decisions in finance, in marketing, and in operations. What you're looking at here is a huge shift in how modern business is done. Over on the left, you see the old way, guesswork, decisions based on intuition, trial and error, a method that is incredibly risky. Now look to the right. This is where we are today, mathematical modeling. This is all about using data to make smart, defensible decisions. And the key idea here is optimization, a formal process for finding the single best possible outcome. This whole approach brings something amazing to the table, predictability. It lets us turn a huge, unknown risk into a calculated, manageable part of our strategy.
All right, let's move on to our second section. Here, we're going to introduce the main mathematical tool for our analysis, the quadratic function. Now, I know that term might sound a little intimidating, but I promise you, its application for modeling all sorts of real-world business situations is actually very, very intuitive.
So, what exactly is a quadratic function? Well, it's an equation that looks like this: y equals ax squared plus bx plus c. The key thing to notice is that little squared term, the x squared. That's what makes it quadratic. And when you graph this equation, you get that classic U-shaped curve we call a parabola. Now, here's why this is so important for us in business. So many of the things we manage aren't linear. They don't just go up and up forever. Think about profit. As you raise your price, your profit goes up, but only to a point, right? Eventually, the price gets too high, people stop buying, and your profit starts to fall. That peak, that's the top of a downward-facing parabola. The same thing happens with costs. You scale up production and your costs per unit go down. That's economies of scale. But if you get too big, things can get inefficient and costs start to creep back up. That lowest point of efficiency, that's the bottom of an upward-facing parabola. Let's translate these math variables into management speak. In our models, y is always going to be the outcome we care about, the thing we want to optimize. That could be profit, revenue, or cost. And x? Well, x is our decision variable. It's the lever we can actually pull as managers, like the price we set or the number of units we produce. Now, the most important piece of this whole puzzle is the coefficient a, the number in front of the x squared. The sign of a, whether it's positive or negative, tells us exactly what kind of problem we're solving. If a is negative, the parabola opens downward, creating what I like to call a profit hill. Our job is to find the very top of that hill. If a is positive, the parabola opens upward, forming a cost valley. And our job is to find the absolute lowest point in that valley.
This really says it all. The entire point of this analysis, our whole goal, is to find one specific point on that curve, the vertex. For us, the vertex is the hero of the story.
It's that single coordinate, that one x comma y pair, that tells us the exact price to get maximum profit, or the exact production level to get minimum cost. It's the answer we're looking for.
Okay, so we've established what we're looking for. Now the question is, how do we find it? That brings us to section 3, finding the optimal point. Here, we're going to roll up our sleeves and use a simple formula to calculate the exact coordinates of that vertex.
It's a really logical two-step process. Step 1 is to find the optimal input. You see, a parabola is perfectly symmetrical. There's a vertical line that cuts it right in half, called the axis of symmetry. The vertex, our peak or our valley, always sits right on that line. The formula for that line is x equals negative b over 2a. So in business terms, this calculation gives us our optimal price or production level. Step 2 is to figure out the optimal outcome, and that's easy. We just take that optimal x value we just found and plug it back into our original equation. The result is the y-coordinate of the vertex, which tells us our maximum possible profit or our minimum possible cost.
Let's make this real with an example. Imagine you're an operations manager. Your company's analysts have figured out that your factory's cost can be modeled by this function. C of x equals 2x squared minus 4x minus 1. In this model, x is your production level in, say, thousands of units, and C of x is the total cost in millions of dollars. Your job is simple. Find the production level that makes your cost as low as it can possibly be.
So let's do step 1. We use our formula x equals negative b over 2a. Looking at our cost function, we can see that a is 2 and b is negative 4. So we plug those in. X equals negative of negative 4 over 2 times 2. Now be careful with the signs. The negative of negative 4 is positive 4, and 2 times 2 is 4. So we get 4 divided by 4, which is 1. Now, and this is critical, what does x equals 1 mean? It's not just the number 1. In the context of our model, it means the optimal production level is 1,000 units. That is the exact quantity that will minimize our costs.
Now for step 2, what will that minimum cost actually be? We take our optimal input, x equals 1, and we plug it back into the original cost function. So C of 1 equals 2 times 1 squared minus 4 times 1 minus 1. Let's work that out. 1 squared is 1, times 2 is 2. 4 times 1 is 4. So we have 2 minus 4 minus 1, which equals negative 3. The coordinates of our vertex are 1, negative 3. The business interpretation? At a production level of 1,000 units, the minimum cost is negative $3 million. Now you might be thinking, wait, a negative cost? In some economic models, this can happen. It could represent a net profit, maybe if you have government subsidies or if you sell byproducts from your manufacturing process. But whatever the context, the key takeaway is that negative 3 represents the absolute best financial outcome you can get with this cost structure.
Excellent. So we've mastered how to minimize costs. Now let's flip to the other side of the profit equation, maximizing revenue. This brings us to section 4, a pricing strategy case study. This is where you'll see how the very same tool can be used to drive growth and boost the bottom line.
All right, here's the scenario. Imagine you're a marketing director. Your company's about to launch a new gadget. Your analytics team has done all the research, surveys, competitor analysis, you name it, and they've created a model for your potential revenue. It's R of x equals negative 5x squared plus 200x. Here, R of x is your total revenue, and x is the price you set for the gadget.
Now hold on. Before you even reach for a calculator, I want you to just look at that function. As a manager, what does this equation itself tell you? What story about your customers and your market is hidden inside this little bit of math?
The most important clue is right at the beginning. The a value is negative 5. It's negative. And because it's negative, we know instantly that this parabola opens downward. This is our classic profit hill model. The math confirms what we know from economics. If you price your product at 0, you make 0 revenue. As you increase the price, revenue goes up. But then it hits a peak. Price it too high and demand drops off, and your revenue starts to fall. So our job is crystal clear. Find the price at the very top of that hill.
So we're going to apply our trusty two-step process again. Step 1, find the optimal price, our x, using the formula x equals negative b divided by 2a. Step 2, calculate the maximum possible revenue we can get at that price, our y, by plugging x back into the revenue function.
Let's do the calculation for step 1. In our function, r of x equals negative 5x squared plus 200x, our b is 200, and our a is negative 5. So the formula is x equals negative 200 divided by 2 times negative 5. That gives us negative 200 divided by negative 10. The negatives cancel out, and we get x equals 20. So the optimal price for our new gadget is exactly $20. It's not $19.99, which is what marketing intuition might tell you. The math says $20 is the price that will bring in the most money.
So, what's the reward for setting that perfect price? Let's do step 2. We plug our optimal price of $20 back into our revenue function. R of 20 equals -5 times 20 squared plus 200 times 20. Okay, 20 squared is 400. Times -5, that's -2,000. And 200 times 20 is 4,000. So -2,000 plus 4,000 gives us a total revenue of $2,000. And I want to be really clear here. This isn't just a guess. According to our model, this is the absolute maximum revenue possible. As a manager, this number becomes your target, your benchmark for success.
Okay, let's move into our final section, and I can't stress enough how important this is, both for your exams and for your future careers. Common mistakes to avoid. It's one thing to understand the theory, but it's another to apply it perfectly every single time, especially when the pressure is on.
I see 3 common errors over and over again. First, the simple sign error in the vertex formula. So many people forget the negative sign at the start of x equals -b over 2a. It's a tiny mistake that leads to a totally wrong answer. My advice, always think of -b as the opposite of b. So if b is already negative, -b becomes positive. The second mistake is a conceptual one, confusing the x and y coordinates. You'll correctly calculate an optimal price of $20 and then say the maximum revenue is $20. You have to burn this into your brain. X is your input, your decision. Y is your outcome, your result. And the final error is misinterpreting the A value right from the start. Your first step should always be to look at the sign of A. If it's negative, you know you're looking for a maximum. If it's positive, you're looking for a minimum. That one little check sets you on the right path for the entire problem.
So, to wrap up, we've built a really solid method for finding the optimal point for any business situation that follows this parabolic curve. You now know how to find minimum cost and maximum revenue with mathematical precision. I'll leave you with a final thought to ponder for our next class. Now that you can find the peak of the profit hill, what other business questions could you answer with this? Think about optimal inventory levels, balancing the cost of holding stock against the cost of running out, or the point of diminishing returns for advertising spending. The applications for this simple, elegant curve are everywhere, and now this tool is part of your arsenal. That concludes our lecture.